Good afternoon to all of you.
Good afternoon, sir.
Everyone is able to see the PPT?
Good afternoon.
Yes, sir.
Yes.
So today we will start our lecture. Till yesterday, we have seen unit number 5 that was related to belt rope and chain drives. Okay. In belt drives, we have seen flat belt drives and V belt drives. Okay. Rope drives and chain drives are for only theoretical treatment. No numericals will be asked on that topic in the examination, right? So just go through those theoretical topics. If you face any difficulty in understanding the topics, you can call me, right? Now today we are going to start our next unit, that is sliding contact bearings. Already in unit number 3, we have seen rolling contact bearings. Right? The basic difference between rolling contact bearings and sliding contact bearings is that rolling contact bearings, they are used for low amount of radial load, low amount of axial loads. Right? But when someone's audio is on, put it off. Someone's audio is on, put it off. Okay. In rolling contact bearings, the contact between the rolling elements was point contact, right? And those type of bearings were used for low amount of radial and axial loads. But if the amount of the load acting on the bearings increases, we cannot use rolling contact bearings there, right? We have to use sliding contact bearings for more amount of radial and axial loads, right? The basic applications where we find sliding contact bearings are in internal combustion engines, right? In turbines, right? There we cannot use rolling contact bearings. Point contact, load transmitting capacity decreases, and therefore we cannot use them, right? Again, the most important difference between rolling contact bearing and sliding contact bearing is that rolling contact bearings are anti-friction bearings. That is, the amount of friction is very less, right, as compared to sliding contact bearings. The amount of starting friction is more, right? Okay, what exactly are sliding contact bearings? As in the nomenclature of rolling contact bearings, we have seen that there is outer race, there is inner race, there are rolling elements. Right? But in case of sliding contact bearings, there is no such thing. Just a bushing made up of a compatible material is used as a bearing in the sliding contact bearings. Right? And the portion of the shaft which is supported in that bearing is called as journal. So in other words, we are also calling sliding contact bearings as journal bearings also, right? Construction is quite simple. It is just like a bushing with inner diameter equal to the diameter of the shaft, which is going to be supported in that bearing, and there must be sufficient amount of thickness for that bushing. So the construction is quite simple for sliding contact bearings. Now, the most important part in sliding contact bearings is the lubrication. In order to avoid metal-to-metal contact between the shaft and the bearing, here you can see the construction of a, this is a typical hydrodynamic journal bearing, right? The inner portion, what you see, is called as the journal. Journal is nothing but the portion of the shaft which is supported in the bearing, right? And this hatched one hollow is called as a bearing, right? It has the diameter. So here it's an exaggerated view, right? Actually, there is a very small amount of clearance between this journal and this inner diameter of the bearing, right? There must be sufficient amount of there, right? In order to avoid metal-to-metal contact of what? The journal and the bearing surface and the journal surface. sufficient amount of lubricant is filled inside the bearing, right? So lubrication plays a very important role in reducing the friction in rolling contact bearings. We all are aware about the definition of the lubrication. It is nothing but it is the science of reducing friction by application of suitable substance. That suitable substance is called as lubricant. And why this lubricant is necessary? To avoid metal to metal contact between the rubbing surfaces of the bodies having relative motion. Relative motion means what exactly? This particular bearing is stationary while the journal inside it is rotating at some speed. Okay, so if we consider this as two rubbing surfaces, so in order to avoid metal to metal contact, we are using lubricant inside it. Okay, so talking about the properties of the lubricants which are necessary for avoiding metal to metal contact, the most important property is viscosity. Okay, again, fluidity, flowability, viscosity index, right? These properties are necessary. Already we must have studied what exactly is viscosity, viscosity index, flowability, either in physics or in fluid mechanics. Okay, similar things are applicable over here also, right? Again, what are the different types of lubricants that can be used? Lubricant can be a solid lubricant, it can be a semi-solid lubricant, or it can be a liquid lubricant. Okay. Uh, in the applications in internal combustion engines and in turbines where heavy amount of load is there, we are preferring liquid lubricants, right, in order to avoid metal to metal contact. Okay, there are basically two modes of lubrication. One is called as hydrodynamic lubrication and second one is called as hydrostatic lubrication. The figure you see on the screen, right, it is a basic hydrodynamic lubrication. There are three figures over here: figure number A, figure number B, and figure number C. Okay, right? At rest condition, the journal is resting on the surface of the bearing. Okay, W is the amount of load, O dash is the center of the journal, and O is the center of the bearing. Okay, so when it is at rest condition, it will look like this. The lubricant is filled over here, right? As the journal starts rotating, right? Okay, due to centrifugal action, it will come towards this center and a wedging action will be formed over there, and the liquid lubricant will flow in that wedge. Okay, you can see it in figure number B and in figure number C. Figure number A is at resting condition, figure number B and figure number C. When the journal will start rotating, some gap will be formed in the surfaces of the journal and the bearing, and the liquid lubricant will flow in that gap. It will be filled. Okay, the gap will be filled by the liquid lubricant in that oil wedge, and metal to metal contact will be avoided. Okay, so based on the amount of film of lubricant formed, we can again go for different things. One is called as boundary lubrication. Boundary lubrication means a very thin amount of film is formed just to avoid metal to metal contact, right? But when the amount of the film, thickness of the film is more, it is called as thick film lubrication. And that thickness of lubricant is what we say, it takes the amount of load which is acting on the bearing, right? So when we say that thick film or thin film of lubricant breaks, right, then the journal surface will come in contact with the bearing surface, right, and metal to metal contact will be there. That means there will be no more lubrication condition and friction will arise over there. So in order to avoid that metal to metal contact, a very thick film of lubrication is necessary, and that is being provided by this hydrodynamic lubrication. Second type of lubrication is called as hydrostatic lubrication, right? In hydrostatic lubrication, that thick film of lubricant is formed by some external means. Here you can see a hole is provided over there, right? And oil is being pumped, right? from oil sump will be there, oil pump will be there. That oil pump will raise the oil from the oil sump and it will push the oil in the bearing and it will try to lift the journal against the surface of the bearing. That kind of lubrication is called as hydrostatic lubrication, right? But again, we can compare hydrodynamic lubrication and hydrostatic lubrication in terms of friction, starting friction, in terms of load carrying capacity, in terms of operating speeds, okay, right? Uh, but if we talk about the comparison on the basis of cost, then hydrostatic lubrication will be more costly as compared to hydrodynamic lubrication because extra accessories are required for the lubrication. For example, oil sump will be there, oil pump will be there, hoses will be there, pipes will be there, and they will become the major sources of the leakages in the system. Okay, therefore, unless and until required, we are not going for hydrostatic lubrication, we are going for hydrodynamic lubrication only. Now, such type of hydrodynamic or hydrostatic lubrication system or hydrodynamic or hydrostatic bearings are capable of taking heavy amounts of radial loads as well as axial loads also, right? Axial loads, for taking axial loads, collars are provided on the shafts so that they do not move in the axial directions, okay? Now, this was about the basic modes of lubrication and basic types of sliding contact bearings. Okay. Now, the important part in this is also regarding the materials that are used for manufacturing these bearings, right? And what are the necessary properties of bearing materials, right? Now, here is the list of 10 important properties that is necessary for the bearing material. First of all, first property is compressive strength, right? Because the amount of load acting is radial, which induces compressive stresses in the bearing material. Am I audible, guys?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
First important property is compressive strength. Okay. Due to the action of radial forces, compressive stresses are induced in the bearing material, and therefore we have to select the bearing material which is capable of taking compressive loads. Second important property is fatigue strength. Due to fluctuations in the amount of load, right? Fatigue stresses or fluctuating stresses are induced, and in order to take those fluctuating stresses, fatigue strength is necessary. Conformability, we all know, we have studied this conformability in case of worm and worm gear materials also. Conformability means the material should be soft enough to conform the material of the journal. Okay, bearing material should be soft enough to take the shape of the bearing of the journal material. That is conformability. Next is embeddability. Embeddability means if there is, say, small amount of friction and some surfaces are being worn out, okay, then those particles should be embedded in the bearing material. They should not cause more harm to the journal surface. That property is called as embeddability. Bondability. Bondability means sufficient amount of bonding strength should be present in the bearing material. Next is corrosion resistance, where we are talking about lubricant. Then lubricant and bearing material, they should be compatible with each other. There must be no oxidation of the lubricant, and if oxidation is present, then there will be corrosion, right? And in order to avoid that corrosion, the bearing material should possess sufficient amount of corrosion resistance. Structure, again, it talks about the strength of the material. Thermal conductivity, if friction is there, then heat will be generated, right? And thermal conductivity is the property which dissipates the amount of heat that is being generated. Okay. Thermal expansion, there must be what we say linear and less amount of thermal expansion. The material should not change its dimension when it is being heated, right? And the last is cost and availability, right? Cost should be less, availability should be more. Okay. Uh, as a design engineer, right, we know that there is no single material which will be capable of which will be capable of having all such properties. But the most compatible materials which are used for manufacturing the sliding contact bearings is, first is babbitt, white metal, right? Babbitt is nothing but it is the alloy of what we say copper, tin, zinc. Okay, that is a babbitt metal. It is also called as white metal. Copper lead alloy, right? Again, copper lead alloy has certain amount of limitations because lead is a poisonous material. Okay, and therefore copper lead alloys have a very limited application as a bearing material, right? But lead has very extraordinary properties than other materials. It is soft. Okay, it has a very excellent embeddability property, but due to its poisonous nature, we are not using copper lead alloys. Silver. Silver is again a very good material having good fatigue resistance, right? But as it is costly, again it has a certain amount of limitations. Sintered metals. Sintered metals means the metals which are manufactured with the help of powder metallurgical processes. They can be also used for manufacturing the bearings. Bronze, aluminum alloy, cast iron, each one has its own advantages and disadvantages. So depending on what kind of application to which it is subjected, we can select the proper material for manufacturing the bearings. So this was related to the lubrication modes. What are the different types of sliding contact bearings? Hydrodynamic, hydrostatic. What are the basic material properties the material should possess for a bearing material, right? And what are the different materials which are used for manufacturing the bearings? Okay. Now guys, next is related to, so you can just go through this. This is say the material from VV Bandari book. Okay, what is viscosity, right? What is viscosity index, right? How the viscosity is measured, Stokes method, and all those are listed over here. You can just go through it. These are the very basic things which we have already studied in, say, physics. Okay. Now, the most important part of this chapter is Petroffs equation. Okay. Petroffs equation. See here, in sliding contact bearings, the sliding friction is more. Starting friction is more because the contact is sliding, right? Unless and until it acquires certain speed, right, journal, it will not come in the center, and a thick film of lubrication will not be formed, right? Once the thick film of lubrication is formed, metal to metal contact will be avoided, and therefore friction should be very less, right? So in order to determine the coefficient of friction in journal bearings, we are using Petroffs equation. So Petroffs equation is used to determine the coefficient of friction in journal bearings. It is based on the following assumptions. Okay, first assumption is what? The shaft is concentric with the bearing. Okay, but actually this is not true. Shaft is never concentric with the bearing. It is concentric with the bearing only in the running conditions and a uniform thick film of lubricant is formed. Then and then the shaft will be concentric. Otherwise it will be eccentric, right? Eccentric means exactly what? The center of the bearing and the center of the shaft, they are not at a same point. There is some difference, radial difference. That radial difference is called as eccentricity. So here the first assumption made by Petroff is the shaft is concentric with the bearing, and second, the bearing is subjected to light load. Okay, so here they have justified their assumptions. In practice, such conditions do not exist. However, Petroffs equation is important because it defines the group of dimensionless parameters. What exactly are those dimensionless parameters? We will see in the next sessions. Okay, dimensionless parameters that govern the frictional properties of the bearing. Okay, a vertical shaft rotating. See here, a figure is given. In this figure, you can see a vertical shaft, right, is rotating inside the bearing. This is bearing. Okay, and the clearance is provided, which is filled with what, guys? Lubricant. Okay, this clearance, right? If I say that capital R is the radius of the bearing from this center, inner radius capital R, and small r is the radius of the journal. Journal means this is called as journal. From here to here, this portion of shaft which is inside the bearing is called as journal. And if the journal radius is small r and the inner radius of bearing is capital R, then we can define capital R minus small r as the clearance. And that clearance will be filled with lubricant. This is the rotation. Rotational speed will be denoted by ns, and the amount of radial load to which the bearing will be subjected is W. The length of journal, right? Length of journal will be equal to length of bearing also. It will be small l. Okay, so these are the geometrical parameters. Small r is the radius of journal, capital R is the inner radius of the bearing, small l is the length of journal, and s is the rotational speed. Okay. Okay, right? Small r radius of journal, small l length of bearing, c is the radial clearance, ns is the journal speed, revolution per second. Now we know that velocity. What is the formula for velocity which we are using in say gears? Each line velocity I dn upon 60. Yes or no? But 60 is just to convert revolution per minute into revolution per second. But as ns is already in revolution per second, so no need to divide it by 60. Okay, pi twice r means diameter, pi dn. 60 is not necessary because it is already in revolutions per second. So velocity, right, of at the surface of the journal is 2 pi r into ns. Okay, right? Now Newton's law of viscosity, second year fluid mechanics. What it is that shear stress is directly proportional to rate of change of shear strain, right? P divided by A is tau shear stress. Okay, du means change in velocity divided by dy means the distance. Okay, it is the rate of change of shear strain, and mu is the coefficient of viscosity. So Newton's law of viscosity can be rewrite as P is equal to mu into A into capital U upon H. Okay, right? Now we will apply the above equation for the viscous flow through the annular portion between the journal and the bearing in the circumferential direction. P is the tangential frictional force. A is the area of journal surface, 2 pi r L. Okay, right? Circumference into length is the circumferential area because we are talking about the circumferential direction. U is the surface velocity, already we have seen 2 pi r ns, and h is the distance between journal and the bearing, that will be denoted by c, that is clearance. Okay, right? So tangential force, right? Here from Newton's law of viscosity, P is equal to mu A U upon H. Okay, mu, right? A 2 pi r L. Okay, then U 2 pi r ns divided by C. Multiplying and rewriting it as 4 pi square r square L mu ns upon C. Then frictional torque is a tangential force into radius, r square into radius, it will become r cube only. So mtf is the frictional torque. Mt, according to VB Bandari, mt is the amount of torque. So frictional torque is tangential force into radius. Tangential force into radius. Force multiplied by radius, r square will become r cube over here. Okay. Now let us consider a radial force W acting on the bearing surface. We know that the unit bearing pressure is force upon projected area. Force is W, projected area is 2RL, right? Okay, 2R means diameter. Diameter into length d into L. It is the area which is supporting what, guys? The load. Okay, so bearing pressure is force upon area. So W is equal to 2PRL. Then again, frictional force. We know that frictional force is equal to mu into R, right? But here mu is denoted as coefficient of viscosity. So we have to think about another notation for coefficient of friction. Coefficient of friction in this particular chapter will be denoted by small f. It will be denoted by small f, and mu will be denoted as coefficient of viscosity or dynamic viscosity or simply viscosity, and small f will be denoted as coefficient of friction. So we know that if we consider, if we talk about the frictional force is mu into R. R is the normal force. Here normal force is W. So frictional force will be coefficient of friction multiplied by W. Coefficient of friction is denoted by F. Okay, so it will be F into W. Okay, frictional force will be F into W. That means that it will be twice FPRL, and frictional torque will be frictional force into radius. Okay, so it will be Fw into R. Fw into R. So it is F 2pr square L. This is again frictional torque. Again, we have seen frictional torque over here. Okay, equating the equation D and the equation F. Okay, you will get, equating these two equations, you will get F is equal to 2 pi square R upon C mu ns upon P. That is called as Petroffs equation. In this Petroff equation, there are three terms. First term is 2 pi square. Pi has no unit, so again it's a dimensionless parameter. R upon C. Okay, R is in mm, C is in mm. So again, it's a dimensionless parameter. Mu is coefficient of viscosity, ns is revolution per second, and P is the bearing pressure. If we equate the units, again you will see that it's a dimensionless parameter, and therefore F is expressed in three terms which are dimensionless. What is this is most important equation, guys. F is equal to 2 pi square R upon C mu ns upon P. Okay, Petroffs equation indicates that there are two important dimensionless parameters, namely R upon C and mu ns upon P, that govern the coefficient of friction and other frictional properties like frictional torque, frictional power loss, and temperature rise in the bearing. Okay, so here we derive the Petroffs equation. Again, in this chapter, it is not necessary. When you are referring VV Bhandari, McKiss investigation is not important. Okay, neither these all parameters are important. No hydrostatic. We will not be dealing with hydrostatic step bearings or hydrostatic lubrication in this chapter. According to our syllabus of University of Pune, we are only interested in hydrodynamic bearings and not hydrostatic bearings. Okay, so this part is not in our syllabus. Hydrodynamic, hydrostatic lubrication. We are only interested in hydrodynamic lubrication. No hydrostatic, only hydrodynamic bearings. Okay, right? Then again, we will start with Reynolds equation for hydrodynamic lubrication. This is the Reynolds equation. Right? How much time is remaining? 8 minutes are remaining. Okay. Like yesterday, send me the attendance by taking the screenshot. Anybody? Okay. Now, Reynolds equation. Okay. Today we will see on what assumptions the Reynolds equation is based. Right? Reynolds equation here, it's a you must have studied Reynolds equation in fluid mechanics also. Right? One-dimensional Reynolds equation, two-dimensional Reynolds equation, and three-dimensional Reynolds equation. It is related to fluid flow. Again, here it is related to fluid flow only, right? Because we are talking about the fluid flow of the lubricant. Okay. So, what are the assumptions made by Reynolds while deriving this equation? The first one is the lubricant obeys Newton's law of viscosity, right? Shear stress is directly proportional to shear strain. The lubricant is incompressible, right? The lubricant doesn't get compressed under the action of the radial force. The inertia force in the oil film are negligible. Okay, we will not be considering the inertia forces. viscosity of the lubricant is constant, most important, right? So we have to select the type of lubricant whose viscosity will remain constant at all temperature ranges, right? Because heat will be generated and that heat has to be dissipated through the surface, to the surrounding through the lubricant only, okay? And therefore the lubricant should not change its properties even when there is rise in temperature. The effect of curvature of the film with respect to the film thickness is neglected. Most important, guys, effect of curvature of the film, right? The lubricant, as it's a liquid, it will take the shape of the surface which is available for its flow, right? But here we are going to consider it as a rectangular element only, and therefore the effect of curvature of the film with respect to the film thickness is neglected. It is assumed that the film is so thin that the pressure is constant across the film thickness. The shaft and the bearing are rigid, they are not deforming under the action of the loads. There is continuous supply of lubricant. Continuous supply of lubricant indicates that there will be a constant thick film of lubrication, right? Because we are talking about hydrodynamic lubrication. Hydrodynamic lubrication means the space between the journal and the bearing will be filled by oil and it will have uniform thickness, okay? So these are the assumptions made by the Reynolds while deriving the equation, okay? Right, 5 minutes are there, okay? See here in this figure, this is bearing and this is the shaft. Shaft is nothing but we are calling it as journal, okay? It is eccentric. O is the center of the bearing, O1 is the center of the shaft, right? W is the amount of radial load acting, N is the speed, okay, right? Again, this particular thickness of oil film is denoted by H. U is the tangential velocity of the surface of the shaft. See, this is shaft now, and this is a tangent drawn, okay? So U is the tangential velocity, and what we are talking while deriving the equation, right, is this particular rectangular fluid element, okay? This rectangular fluid element which is shown over here, right? See here, you can see this rectangular element, okay? This is bearing, this is shaft, okay? The directions are shown over here. This is Z direction, this is Y direction, and X direction will be from this point towards the perpendicular to the plane which we are looking, right? So this will be the three directions, X, Y, and Z directions, okay? And this, we will be focusing on this rectangular element, okay? The rectangular element in XY plane is shown over here, right? You must be remembering when we were deriving the equations for incompressible fluid flows in fluid mechanics, P, then incremental amount of P plus dabba P by dabba X with respect to dx direction, right? This is shear stress, this is bearing surface, okay? So shear stress and incremental amount of shear stress, right? So equating all this thing, okay, you will get first equation dx dy dz dx dy dz, as it's a volume, so it will get cancelled. So equation will be dabba tau x upon dabba y is equal to dabba P by dabba X, okay, right? Again, using Newton's law of viscosity, right, we can modify this equation taking derivative, right? Boundary conditions, applying the things, you will get first equation as this one, small u is equal to uy. This will be in xy plane. Again, similarly, we can go in z direction and you can have another equation. This is in yz plane, okay? You will get w is the velocity in which direction? Z direction, okay? You will get this equation, right? There will be no equation in y direction because there is no flowing of lubricant in y direction, okay? So in x direction, this is the equation. In z direction, this is the equation, okay? Using the continuity equation and simplifying the things, okay, you will get a Reynolds equation in this particular format, this equation, okay? In examination, we are not expecting the derivation of Reynolds equation, and neither we are bothered about the application of this, direct application of this Reynolds equation, but just for your knowledge point of view, there exists a Reynolds equation for the lubricant. Okay, right? In tomorrow's lecture, we will see how this Reynolds equation is further used in the analysis of the sliding contact bearings. 1 minute is left, guys. Hope you must have understood today's lecture.
Yes, sir.
Now, just open the book of V.B. Bhandari, or either you can open the book of R.B. Patil also. In R.B. Patil, right? R.B. Patil means the Tech Max book. Okay, certain things are given related, basic things are given related to lubricants, lubrication, right? What are the properties of lubrication? You can just go through that. And those who are referring V.B. Bhandari, you can refer to this PPT. I will share this book with you either on WhatsApp or Google Classroom. Just go through these things. Okay, guys.
Yes, sir.
Bye for now. Good day. Stay home, stay safe.
Thank you, sir.
Yes, sir.
Don't roam here and there.
Yes, sir.
Chalo, bye for now. Stay.
तिकडे जा.
कोणीतरी अटेंडन्स पाठवा रे मला तेवढी.